Hello everyone, this is Dr. C. Pre-lecture today will focus on Gibbs free energy. So let's just get started. So for our purposes, what we're really going to use this for is we're going to use this as another method. Oh, sorry, I need to get a pen here to predict spontaneity. We've already looked at using the second law of thermodynamics. Now we have another way that in a lot of ways is a little bit easier because it only focuses on the system. And if you look down at this third bullet point, we're always interested in the free energy change as we go from reactants to products. How does it change over the course of the reaction? So this is the equation we'll focus on, at least for part of this pre-lecture. And realize I could write reaction or system for each of my terms in this equation. The nice thing about this is we just need to focus on our reaction. We need to focus on our system. Okay? Now, the sign conventions in this chapter can be a little bit confusing because we need to know sign conventions for the enthalpy change. We need to know sign conventions for the entropy change, for, say, the entropy of the universe for second law of thermo. We also need to know this for delta G, of course. And so make sure you're aware of this, that a negative delta G, okay, so if we have a negative delta G, that would indicate a spontaneous process in the forward direction, reactants going to products. All right? If you have a positive sign of delta G, okay, clearly then that would not be spontaneous in the forward direction, but if we were to reverse the reaction, it would be spontaneous in the reverse direction. Okay, so we can always, in our minds, if a reaction is not spontaneous in one direction, it would be spontaneous in the other direction. We'll mention this later in the pre-lecture, delta G of 0. That would indicate that the system's at equilibrium. Okay, system's at equilibrium. But focus right now on negative, spontaneous in the forward direction, positive, not spontaneous in the forward direction. All right, so our sign convention, as I talked about already, is really important. And so just knowing the signs of delta H and delta S will allow us to predict spontaneity in a couple of cases. So there's two cases, the first two that are presented here, are cut and dried. If we have, in the first case, an exothermic reaction that leads to an increase in entropy, okay, so a negative delta H, exothermic, a positive delta S, so these two situations, we will always get a negative delta G. And make sure you can convince yourself of that. Look at our free energy change equation. If we have a negative delta H minus a positive delta S, we will always get a negative delta G. So this reaction is spontaneous in the forward direction at all temps. All right, that's all there is to it. The other situation is the opposite. We have endothermic, leads to a decrease in entropy. Right? We will always get a positive delta G, and that would indicate it's not spontaneous at any temp, any temperature. Okay, so those are the cut and dried situations. And the one way I encourage you to think about this, you can always think about it in terms of the sign convention. So for this one, with a positive delta H minus a negative delta S, we will always get a positive delta G. So you can always do it by sign convention, but in some ways I'd like you to think about it in terms of favorability. We think of reactions that release heat, exothermic, as being favorable. Okay. Reactions that lead to an increase in entropy, more disorder, favorable. All right. If both quantities, heat flow and entropy change, delta H and delta S, are favorable, spontaneous at all temps. If conversely they're both unfavorable, endothermic, we have to supply energy from the surroundings, it leads to more order when we form the products, decrease in entropy. Those are both unfavorable. That type of situation is not spontaneous. All right. Now, situations 3 and 4. One favorable, one unfavorable. So, for example, third situation, we have exothermic. Favorable heat flow, decrease in entropy, unfavorable. Just by looking at the sign convention, we cannot predict delta G. Because we need to know something else. And what is that? We need to know temperature. These last two processes, situations, will be temperature dependent. Okay? So we're going to look and at least mention at the end of this pre-lecture how we can figure out at what temperature one of these would become spontaneous. We will also talk about how to predict, does it become spontaneous as we raise the temperature, or does it become spontaneous as we lower the temperature? That will become important. But these two situations, one favorable, in this case exothermic favorable. Oh, God, I hit the wrong button. Sorry about that. Favorable, and then an unfavorable entropy change. Okay, one of each, so to speak, temperature dependent. Same thing for situation 4. Unfavorable heat flow, endothermic, but a favorable entropy change, more disorder, increase in entropy, that will also be temperature dependent. So think through these sign conventions. Make sure you know sign conventions for delta H and delta S and how those go together. There will definitely be a question on the pre-lecture quiz regarding these sign conventions. One thing for fun you might want to try, just for giggles, okay? This is to represent, you can represent these rubber molecules as a rubber band. Okay, so if you have a rubber band hanging around, you might want to grab it. And so if you just pick up a rubber band, this is kind of at least, a drawing, what the rubber molecules look like. Rubber molecules are very long molecules. And when that rubber is contracted, the rubber molecules are all kind of jumbled together. They're pretty disordered. Okay? Then take that rubber band and stretch it out. So stretch. And what we're going to do is, what we're going to cause to happen is all those rubber molecules are going to align with one another. Okay? So this is more ordered. Okay? So that is a decrease in entropy as we stretch out a rubber band. But what about delta H? Okay? Now, so you stretch out the rubber band, the rubber molecules line up, and my rubber band that I had in front of me just broke. How about that? I know you can see that. So I stretch out my rubber band, and it's hard to tell the heat flow, but if you actually hold it up to your say your top lip, your top lip is pretty sensitive, and you should be able to feel what happens. I know you're all doing this. You're going, Dr. Cruikshank, you're crazy. Okay? And what you should feel is you should actually feel that rubber band warm up. This is actually exothermic. Okay? So if you're thinking about favorability, we have one favorable, one unfavorable. Now you can tell that direction, stretching the rubber band, wasn't spontaneous at room temperature. You had to force that to happen. You had to use your own energy to stretch that rubber band out. But going the other direction becomes more disordered if we go back this way. So let it contract. It's going to become more disordered. That's favorable. But if it's exothermic stretching it, what's the delta H if we let it contract? Oh, and I'm kind of off the page here. I apologize. It's going to be endothermic. So again, this will be temperature dependent. Okay? At room temperature, it's actually spontaneous going back this way. And I'm sorry, my writing, I need to be a little more organized here. I apologize. It's spontaneous going back this way. You stretch it out, it's going to spontaneously snap back. Okay? At room temperature, it is spontaneous. And you can feel the same thing. Stretch it out, you'll feel it warm up, and then hold it against your upper lip and let it contract, and you'll feel it cool down. That's endothermic. Okay? The energy was actually taken from your body for that reaction. And that's why it feels cooler, because you had heat flow out of your lip into the rubber band. Pretty cool. Pretty simple, but play around with it. It's kind of fun. Okay. Not to waste any more of your time. We're going to look at two ways to calculate delta G. Here's that equation again. We could plug in delta H. We could plug in delta S. You may have to calculate them. Remember, these are the system or reaction. We know how to do that already from delta H of formation values or standard entropy values. Sometimes the problem might give them to you directly, delta H and delta S, just plug in and solve. You do need temperature as well. Temperature in Kelvin. All right. One word of caution. Your delta H is typically in units of kilojoules, and your delta S is typically in units of joules per Kelvin. You're going to have to watch those units when you do this calculation. Okay? Next method. So there will be one question in the pre-lecture quiz using that equation to calculate delta G. This equation should not surprise you. Calculating delta G from delta G of formation values. Looks very similar to calculating delta H or delta S, right? You know how to do that. There will be one like that in the pre-lecture quiz. So that's 3 questions. Maybe we'll leave it at 3. I do want to point out about delta G of formation, just like delta H of formation, if it's an element, okay, so composed of only one type of atom, and it has to be in its most stable form at room temperature, it has a delta G of formation of 0. Sodium at room temperature exists as a solid, a metal, 0. Fluorine at room temperature exists as a gas. It also exists as a diatomic gas, delta H or delta G of formation and delta H of formation of 0. Mercury exists as a liquid at room temperature, delta G of formation and delta H of formation of 0. You can look these up in the appendix of the book. More likely than not, you'll look them up in Sapling. And the last thing I want to do with the pre-lecture day, I'm a little over 10 minutes, so I'm about to wrap this up. I just want to show you one thing that we can do with this delta G equation. Okay, one thing we might want to figure out is temperature at which reaction becomes spontaneous. So remember, there were 2 cases we started this pre-lecture with. If delta H is negative, delta S is negative, or they're both positive, that will be a temperature-dependent situation, okay, depending on the reaction. So temp at which reaction becomes spontaneous. All right? Now, we really want to know when delta G becomes negative. But what negative number do we choose? -1, -0.1, who knows? Okay, so what we do instead is we say, well, let's set delta G equal to 0, because that's right when delta G is about to become negative. So if we set delta G equal to 0, okay, we can then rearrange this equation, bring T delta S over to this side of the equation, solve for temperature. Okay, delta H divided by delta S. Now remember, this is system or reaction in both cases. So we can for the temperature-dependent situations, and make sure you know what those are, we can very quickly solve for the temperature at which a reaction becomes spontaneous. We'll do that. I'm not going to put that on the quiz, but we'll work one of those in class, and we'll talk about, it depends on which situation is. Is it negative for delta H and delta S? Or positive for delta H and delta S? Does it become spontaneous as we raise the temperature, or does it become spontaneous as we lower the temperature? We'll talk about that. Again, watch your units here. Delta H is typically in kilojoules. Delta S is in typically joules per Kelvin. You're going to need to take care of that when we do that calculation. Okay, I think that's enough for now. I didn't work any problems, but I will give you a problem to solve for delta G a couple of different ways in the pre-lecture quiz, and the question about the sign conventions as well in the pre-lecture quiz. And I think that'll be good. I will see you in class very soon. Take care.